Okay, how are you? So, my name is William Nebinger Tobin, and I'm doing my malware analysis practical 4 report today on Necro. So, first off, thanks for joining me. Really excited about this, and I learned a lot about this very cool piece of malware. So, I'll go ahead and get right into it. So, to start off, the simple and most basic way to describe this is that Necro is a botnet malware. So it communicates with other devices, it has command and control, it has networking capabilities, etc. Something really unique about it is that it's written in Python. It ends up being about 1,500 lines of code. And for the malware samples that I was exposed to, they were LSB Linux executables, although from researching other reports, I found and learned that it's actually also commonly deployed on Windows systems. And I have some theories for why that might be beyond just, I didn't find the other types of executables. For example, it does actually write some Java code, which I'll talk about later in this presentation. So yeah, it spreads via networking, and it automatically exploits vulnerable machines. Again, what will be talked about in this presentation is you can actually find what looks like a list of vulnerable system components, for example, types of Mozilla, types of Chrome, that actually make vulnerabilities that it can find and then exploit to gain access to other systems. Like I said, it has command and control. I'll talk a little bit more about that and how it works. And it also has a very interesting, what I would consider more of a persistence mechanism, but it's sort of more a persistence mechanism, obfuscation, and anti-debugging at the same time. And I'll explain why that is further into the presentation. All right. So moving forward, I'll just talk about some of the imports, some of the basic imports that you'll learn. It really doesn't have a lot. And again, I have access to the source code at this point, fully decompiled, so I can see everything about it. And it has about 20 imports. The first ones that relate to networking are URL lib, SSL, and SHA-512. With some research I've done in some other security classes, I know that SHA-512 is commonly used for key generation to set up symmetric key encryption. And similarly, SSL is used as a secure library, so to speak, for encryption, etc. So my guesses here right off the bat is that this is using some sort of SHA-512 for key generation, and then it's using SSL with some sort of encryption. And so it also contains imports related to execution. This is sort of trivial. In every malware sample that I've analyzed, I found this. There's always some sort of threading, some sort of sub-processes, multi-threading. It always operates with the OS, spawns processes, system calls, etc. And then the reason for this threading with this program, most of what it does is networking with its command and control, and also exploitation, and then it does read-write some files on the system. So, when it's multi-threading, it's doing all these things at the same time. The last really important import that I found was the zlib import, which is what's used for its quasi-obfuscation, I would call it. And it basically is just used to compress, or in this case, really to decompress binary data that is encrypted with a key used to make this malware difficult to deal with. So you can look here. This is actually all of the imports it has. As you can see, it's written in Python 2. It's got some base 64 encoding decoding. It's not really too interesting. Random. It does use random throughout the code to, I don't want to sound trivial here, make random choices when it needs to. Sometimes it has to pick out random URLs, or it has to, from some list of ports it has to randomly decide which one to use. And it also uses this when it reaches out to the command and control. I should talk about this later, but it looks for random CNC servers, so it's not hard-coded into it, and it's very difficult to guess what server. But if you actually go through and you use the same algorithm that it uses to look for what command and control server would be up, you can actually go and find some of them that, if you look long enough, you'll find one that is up. And this is from a research paper written about 6 months ago, so I don't know how active it is. I was not courageous enough to try it, but you can go use as random to do a lot of things. Anyways, okay, so now to talk about strings. So this was difficult since this was LSB executable, and since it was written in Python, I couldn't just throw it into PE Studio and get all the strings out of it, which would have been nice. And unfortunately, as I'll explain later, all the strings in this are actually encrypted with a new key every time that the program is run, specifically to make it difficult for the user to be able to hash it and find it. So that's sort of why I say it's a persistence mechanism, and I'll talk about that later. But so yeah, once you decrypt it and you go through everything, you can find a ton of strings related to IP addresses and port numbers. The way that this actually works is a bunch of these IP addresses, one list of them where they're stored, are all actually Tor IP addresses. So it uses the Tor relay to get in touch with its command and control server. Fair enough, that kind of makes sense. If I were to write a botnet, I'd probably do the same thing. Similarly, there is a certain way, and this was found through research papers, and it's actually in the code and in my report where I reference it and talk about it, is that it does use, like I was just talking about randomly, it does search for what a command and control server could be up, and basically hunts it down and gets in contact with it. There's a string of Java code. This is not in this presentation, but it is in the report. And it's basically a piece of Java code that does networking stuff, which is how I think it could come around to relate to Windows, assuming that there's not another type of executable that I didn't find, which there probably is, but this definitely, sort of guarantees that. A very funny long list of username and passwords were found. So like Linux admin would be like a username password pair, and then a bunch of trivial stuff, which is also shown in the report. Another one in the report, and not this slide for space constraints, is that there is a long list of what looks to be vulnerable systems. So it might say Mozilla Firefox 10.1. I'm making this up. Chrome 9.2. And then it also has what appears to be names of exploits that it can use to actually get in. So yeah, here's just a basic sample. These are actually the Tor IP addresses. And these are these are the first ports it scans. And so yeah, these are the initial Tor where it connects and looks at it. And I changed some variable names to make it easy. But yeah, these are the Tor addresses that it uses as its relay. Again, there's so many pictures of these strings. Please check out the strings that are in the report. Give you a lot more insight into what's actually going on. Okay. So I say here, obfuscation, persistence mechanism, anti-debugging. Maybe I should just show you what it looks like first. So this is what the code looks like before you do anything to it. So it's binary data, it's decompressed, and then it's run through whatever this function is here, right? So I say that it's all these things because it's kind of obfuscated. It is a persistence mechanism when you understand why it's doing this at its core, and it's also anti-debugging. Not so much in the sense that it sets a flag when it debuggers up and keeps it from stepping through, but in a sense that when you're looking at this code, unless you go through and do this, you're really not going to learn anything about it. So with that said, here is how it's a persistence mechanism, and that is after each execution, Necro chooses a new key and uses it to encrypt all the strings in the program. Sound fair enough? It's basically what it does. It gets a new key. It has this function here right before the zlib.decompress, and you essentially have to decompress the binary data, and then you have to run it through the function, and you have to have the key in order to be able to actually turn that into a string. So this is an obfuscation method in the sense that it does turn a string into binary data. It's, whatever. And the main goal of this is that it makes the hash undetectable. So this actually gets changed every time it's run. So every time it runs it, this little string in here is going to be different based on the key chosen. And so that makes it really hard for malware analysts to find this. So I propose a Yarrow rule at the end of it and kind of talk about why that's going to work better than any hash that you could find, because the hash is going to change every time. Makes it very difficult, more like impossible, to debug the program without decrypting all the strings. I mean, I guess you can run it, but if you really want to learn anything about it, you're gonna have to take a good look and you're gonna have to read the code and figure out what's going on. So you really do have to find a way to get over this obfuscated code and figure out how to really take an in-depth look at it. All right, so here's another picture. Don't think we need to look at this anymore. Okay, so now you're probably asking, well, okay, like how do you get over this? How do you deobfuscate this, and how do you actually be able to take a look at it, which ends up being the game changer, right? So to deobfuscate the code, I wrote a Python program that uses regex, and I found the key and the decryption algorithm. They're very cleverly hidden in the code directly at the top of it. So anyways, the code was then run. I ran my code on the necro.py file, which basically goes through and looks at every place where it's encrypted, and with the stolen key and the stolen decryption function, I was able to make a new file that you can look at very easily. Also, upon the deobfuscation, you're obviously able to read and write it. Along with this submission, and if I put this on YouTube, I'll go ahead and I'll put my completely deobfuscated code up so you can take a look at it for anyone else out there other than my professor that's interested in learning about what the code actually looks like. All right, so this is actually the code used to do it. Excuse this guy's French, but he has a decode string. It's really a key. Screw spy tech users, we the militia, nani moose. So that's the key that was used here. My guess is that this hex value, this x65, is what really makes this difference. So actually in my YARA rule, it looks for just the end of this. And you should almost always be able to find it. So anyways, the decode, it does a join on an array, and it casts to a character the order of C, raised to this exponent for IC and enumerate S. Don't quote me on it. It looks a little bit like some sort of public key encryption. I didn't check that out, but it's what it looks like. So I wrote some helper functions here. I guess I'll start with my main so we understand what's going on. So I open the file, I read all of it, I join it all to one, and I close it. Then I use the regex to substitute anything with the name of that bizarre function, followed by a quote, a call to that function with the zlib decompress. This is some nasty looking regex that basically says anything between two parentheses. Anything in quotes between two parentheses is exactly what this does. And then I make a call to my fixexp, fix encryption call. This is a function pointer to this function that calls whatever string is found in this, and it's done on the file on Necro. So what happens is this takes a match object. When it finds a match, it substrings it from 28 to -3. So basically what it does is it finds exactly where that quote is. It switches it to hex. This is necessary to be done for there's a very specific reason why you have to do that. It's not really important here, but some issues can be done when it parses the file. It escapes every backslash here, so it gets 2 backslashes. So then you're trying to decrypt that as a string and not as binary data. So you have to switch it to hex and basically get it back to binary data. That's why you can see I break off all of those and I cast them to characters within the hexadecimal range. And I return that as a string. Once I do that, I zlib decompress it just like it does, and then with the stolen decode function, I decode it, and with the key and everything, it switches it into all Necro. I open a decoded Necro, and the rest is history. I write it. All right, so here's the YARA rule. Again, excuse this guy's French. This is, got the F word in a function on a school report. Well, I can't help it. So here's the rule. So the strings, the one string that's like a telltale to this program, I'm pretty sure about it, is this wonderful, wonderful string right here. This basically says anything preceding screw spy tech users, we militia, blah, 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 and then condition it on finding this key. I highly doubt this key's anywhere else. I could be wrong, but I'm fairly confident this is going to be a really strong indication of whether or not you're actually going to find. This will be a really good indication of whether or not it's actually Necro on your machine. So yeah, like I just said, that's what it does. The hash is useless. It's not really any reason to put a hash here. You're not going to find the same hash twice. Every time it runs, the program changes itself. So use the Yarrow rule. If you're actually analyzing this and you want to find it, use the Yarrow rule. So that brings me to the end of the presentation. I really hope you learned something from it. Again, there's a lot more details in the written report. And as well, I'll go ahead and I'll put up the decoded Necro code on a GitHub for anyone to look at if they're interested. And yeah, thank you for watching. I really appreciate you taking the time to check it out. Take care, everybody. Thank you.